Welcome to our next chemistry lesson. This lesson will focus on enthalpy. So, what is enthalpy? Well, let's start by talking about exothermic and endothermic reactions. Now, most reactions you'll run into will either absorb energy or they'll release energy. So an exothermic reaction is a reaction that releases energy. So we actually have energy on the products side of the equation. So for example, when you take hydrochloric acid and you mix in sodium hydroxide, you get water, salt, and a bunch of energy released. Endothermic reactions are reactions that absorb energy. So the energy winds up being on the reactant side of the equation. So for example, in photosynthesis, we have carbon dioxide and water, and energy combines together to give us C6H12O6 and oxygen. So remember, energy is never consumed or destroyed, it's just transformed in form. So it isn't really that an endothermic reaction uses energy, it just simply stores it, it absorbs it. And then an exothermic reaction simply releases the energy that was absorbed. So enthalpy, the term by itself, refers to the energy stored in a substance, and it's represented as H, and this is measured in kilojoules. So we previously talked about joules, which is a unit of energy, and so a kilojoule is just 1,000 of those. We usually don't measure enthalpy by itself. We measure the difference in enthalpy between two products, and that will tell us how much energy is absorbed or released. So when the products of a reaction store a different amount of energy than the reactants, we call this a change in enthalpy, or delta H. So if delta H is positive, then the reaction is endothermic. What that means is that the products are storing more energy than the reactants. So we're going to have to use freely available energy at the beginning of the reaction in order to accomplish that. We have to absorb energy. Delta H is negative when the reaction is exothermic. So if the products are storing less energy than the reactants, well, that means the energy is coming out. And so there's more energy that's freely available at the end. Now, sometimes in a kind of sloppy use of terminology, people will refer to the term enthalpy as delta H, or they'll call that the enthalpy of the reaction. And this is actually, it's just a sloppy use in terms. Since H is rarely itself utilized, and it's almost always delta H, usually the word enthalpy oftentimes gets attached to delta H, since H isn't really used very much. But really, delta H is the change in enthalpy, not the enthalpy itself. But as I said, sloppy terminology, people will oftentimes use the word enthalpy to refer to the actual delta H and not just H. So, measuring enthalpy. So there's two ways to measure enthalpy, and we'll talk about both of them. You can either measure them by looking at the bonds in the products and the reactants, and looking at the energy that's released when forming each of those, or you can calculate the energy of formation of the products versus the reactants. And we'll talk about both of those coming up. So let's start out by talking about how do we measure enthalpy with bond energies. So let's start with a simple reaction. So we're going to have, this is how H2O is formed. It starts with elemental hydrogen, which is H2, and elemental oxygen, which is O2, and they combine to form H2O. So let's look at all of the bonds on the left-hand side. So we've got, so if you were to draw this out in a Lewis diagram, you will see that the H's have a single bond between them, and we've got two H2s, so that means both of those have single bonds between them. And then the O the O2 has a double bond between them. Okay, so now let's look on the product side. Well, we've got two H2Os, and so each of those have two single bonds between hydrogen and oxygen. Okay, now what happens when the reaction occurs? Well, we've got to break all the bonds from the reactants and then build all the bonds on the products. Well, it takes it takes energy to break bonds, and energy is released when bonds are formed. So we're going to have to put in energy to break this bond. We're going to have to put in energy to break this bond. We're going to have to put in energy to break this bond. And then when the products are formed, energy will be released when we form this bond. It'll be released when we form this bond. It'll be released when we form this bond, and it'll be released when we form this bond. Okay, so when we break bonds, we're absorbing energy, and when we're forming bonds, we're releasing energy. You see that? So this is a little counterintuitive. You might think that the bonds themselves might store energy, but they don't. It actually takes energy to break bonds. Energy comes in and is absorbed to break the bonds. And when the bonds are formed, that releases energy. All right? So to calculate enthalpy using bond energies, well, we have, so the amount of energy it takes to break a bond and how much energy it takes to release a bond, those are actually the same, just one's positive and one's negative. This is known as the bond energy. So when calculating the delta H of a reaction, you add the bond energies for the bonds that are broken, because energy was absorbed to break those bonds, and you subtract the bond energies for the bonds that are formed, because this is the energy that was released when the bond was formed. And you need to be sure that your calculation includes all of the bonds. Don't forget to include the coefficients from each side of the reaction. Okay, so here's a sample table of bond energies. So you'll notice you don't need to remember these. You can look them up. Whatever chemistry textbook you're using will have a table of bond energies. And you know, the different tables will be slightly different just because you know, depending on who you ask and how the experiment was done, they might have slightly different energies for each of the bonds. But anyway, this is a sample table that you might find. And so you can see that the bond between a hydrogen and a hydrogen, a single bond between a hydrogen and a hydrogen, is about 432 kilojoules per mole. So that means that since our chemical equations are basically done per mole, each of those bonds that you find will represent 432 kilojoules. And so if we've got a double bond between oxygen and oxygen, that represents 494 kilojoules. So let's do the calculation. So we have to put in 423 kilojoules to break that bond. And that's actually, we have to put in 432 kilojoules to break a mole of that. And since we've got 2 moles, we've got to do it twice because we've got 2 H2, and that represents 2 moles of H2. So we've got 423 kilojoules to break each of those bonds. Then it takes 494 kilojoules to break a mole of those oxygen-oxygen bonds. Now, when the hydrogen-oxygen bonds are formed, we're going to release 459 kilojoules per mole. And we're going to do that 4 times because we've got 4 of these. Okay, so that represents all of our bonds being released. Now, remember, this is not per atom, this is per mole. Okay, so for every mole of these bonds, we're going to have 459 kilojoules released. So in this equation, the right-hand side has 2 moles of H2O, so that means we're going to wind up having 4 of these 459 kilojoule events. So, so for your reaction enthalpy, we're going to calculate that by, so we're absorbing the energy on the left, we're going to release the energy that's on the right. So, and because it's negative, that means it's an exothermic reaction. So, to review, when we calculate delta H with bond energies, we're going to draw the chemicals with their bonds. Okay, that's going to tell us, so we're going to use our information that we know from Lewis structures and bonding to figure out how our chemicals are bonded together, or we're going to look them up, one of the two. And you do that for both the products and the reactants. And then we're going to look for each of the bonds in the chemicals. And so we're going to calculate the bond energies of each bond in both the products and the reactants. Okay, and so we're going to recognize that energy is absorbed when bonds are broken, and they're going to be released when bonds are formed. Therefore, we add the bond energies of the reactants and we subtract the bond energies of the products, and the result is the delta H of the reaction. All right? So that's one way of calculating delta H. The other way of calculating delta H is with the enthalpy of formation. Okay, so we're going to start with this thing called Hess's law, and this sounds confusing at first, but that's okay. Just hang with me for a second. Hess's law states that the reaction enthalpy is a state function. Okay, well, what is a state function? So to understand state functions, let's take an example that's completely divorced from chemistry. Let's imagine that I'm in Tulsa and I'm driving to Denver. Okay, so there's a little map, Tulsa and Denver. So let's say that I care about the total change in elevation from Tulsa to Denver. Well, the total change in elevation is a state function. And what that means is that it doesn't matter if I go to Denver via New Mexico and go through Raton, or if I go through Kansas and go through Wichita. That whichever route I take, if I take this route, if I take that route, it doesn't matter which route I go through, the total change in elevation from Tulsa to Denver will be the same. So that's what it means to be a state function. So it doesn't matter what path that I take, the total change that I'm looking at, the thing that I'm looking at, no matter what the path that I'm taking, will be the same. So let's say that I don't know the elevation of Denver, but I know the change of elevation from Tulsa to Wichita and from Wichita to Denver. Okay, so if I know those two changes, I can tell the total change in elevation from Tulsa to Denver. Okay, it doesn't matter if Wichita goes down or Wichita goes up. If I know the change from Tulsa to Wichita and from Wichita to Denver, then I can know the total change from Tulsa to Denver. Since total change in elevation is a state function, that means this will continue to be true even if my actual route, I decide to go through Raton to Denver. That's not changing the difference in elevation between Tulsa and Denver. It's just giving me a different route to go. Okay, so no matter which path I go, the total change in elevation is going to be the same. So that's what it means to be a state function. Okay, and this is important in chemistry because we may want to measure something and we don't know what the intermediate products of the reaction are. So we can figure this out if we know some possible intermediate steps, if we know some places that it could go and we know the differences between them, we can calculate the total difference. Another way we can do this is if we have a standard location. And in maps, we usually do this with sea level. Okay, so sea level is kind of considered our 0 point. Okay, so if we have a point like on the coast and we mark that point as 0, so we call that sea level. And so if I say that Tulsa is 722 feet above sea level, that means the total change in elevation from me driving to Tulsa to me driving to sea level is going to be 722 feet. Likewise, if I know that Denver is 5,280 feet above sea level, then that means that if I drive from Denver and I drive all the way to the coast to the sea level, that's going to be a 5,280 feet change. And so since I know both of those, I can actually figure out the total change in elevation between Tulsa and Denver by subtracting them. And so this is going to be true whether I actually drive to sea level both times or not. Even though both of them are measured in relation to sea level, because total change in elevation is a state function, I don't actually have to take that path to sea level to know that the difference between the distances is going to be the same no matter how I travel. So state functions allow us to create standard markers that we can use. In this case, it's standard elevation, elevation above sea level. That's the standard marker that we're using. And if everybody is measured in terms of that same standard marker, we can tell the differences between the different locations simply by taking their standard elevation above sea level and subtracting them. And so this is very similar to the way that we're going to be doing calculating enthalpy. And this is using what's called enthalpy of formation. So what enthalpy of formation does is it's expressed as delta subscript F, capital H, and then the little degree symbol. The enthalpy of formation of a chemical is the delta H between the elements in their elemental form and the complete chemical, such as H2O. Okay? And the reason that we have this enthalpy of formation is because it's actually fairly it's fairly straightforward to measure the enthalpy of formation in a laboratory. So people in labs have calculated the enthalpies of formations of all sorts of different chemicals. And so they have tables of them, and we can simply look up the enthalpy of formation that we are looking for in a table. Now, because delta H is a state function, if I know the enthalpy of formation of the products, and I know the enthalpy of formation of the reactants, then I can simply calculate the delta H between them. Okay, so this is basically what I'm saying, is that if we know how much energy it takes to go from basic elements to your reactants, and we know how much energy it takes to go from basic elements to your products, well, we can just pretend that however the reaction goes, that it goes from the reactants to their elemental forms and then back to their products. Now, it doesn't have to actually do that. Just like if I'm measuring driving from Tulsa to Denver, I don't actually have to drive to sea level and then drive back to Denver for those calculations to be correct. The calculations are correct no matter what the actual sequence of events happens. As long as I know the beginning point and the ending point, I can use these standard enthalpies of formation to calculate what the difference is. So let's take an example. Let's say we have HCl plus NaOH, and that goes to H2O plus NaCl. Well, looking it up in tables, the enthalpy of formation of hydrochloric acid is negative 166 kilojoules per mole, and I have 1 mole of them in my equation, plus NaOH. Okay, and so the enthalpy of formation of NaOH is negative 426 kilojoules per mole, and I've got 1 mole in my equation. H2O is negative 286 kilojoules per mole, and I've got 1 mole in my equation. And NaCl is negative 411 kilojoules per mole, and I've got 1 mole in my equation. So what I do is I simply add up the enthalpies of formation of my products, and I subtract the enthalpies of formation of my reactants. And that will give me a final result of negative 105 kilojoules for the reaction. Okay, and so this final one is not kilojoules per mole because this is the total amount of kilojoules released with the reaction on the left, assuming that we have each of those represents 1 mole. So here's just some sample enthalpies of formation, just to give you an example of what they look like. Most of them are negative. Some of the gases are positive. And then you'll notice at the bottom, elemental hydrogen and elemental oxygen have enthalpies of formation of 0. You might wonder why that is. Well, because the point that we're measuring against is the elemental form. And so it's like sea level is at 0 because sea level is what we define as 0. And so likewise, since H2 is the elemental form of hydrogen, well, then the distance from the elemental form of hydrogen to the elemental form of hydrogen is 0. Okay, so just to kind of hammer that point home a little bit, if we look at our water example, Okay, so we've got 0 kilojoules per mole and 0 kilojoules per mole on the left, so both of those are elemental. And then on the right, we've got the enthalpy of formation of H2O is negative 286 kilojoules per mole, but we've got 2 moles of it. That will be 2 times negative 286, because we've got 2 moles, minus 0 is negative 572 kilojoules. And so that means that this reaction will release 572 kilojoules worth of energy. Now note that this is a little bit different from our previous result, and the reason for that is that enthalpies of formation are more exact than calculations using bond energies. So usually if we know it, it's preferable to use enthalpy of formation, but if you don't know the enthalpy of formation of something, you can use bond energies as an estimate. So all this has been stated under Hess's law, and so here's just a mathematical statement of Hess's law. And if you notice these little degree symbols, they just mean that these occur on standard conditions. So the change in enthalpy when we're at standard conditions is the sum of the energy of formation of the products at standard conditions minus the sum of the energies of formations of the reactants at standard conditions. All right, so now let's work on putting this information to use in an actual equation. Okay, so we're going to use our change in enthalpy in our reaction equations. Okay, so first of all, we noted at the beginning that if delta H was positive, then energy is a reactant. If delta H is negative, then it's a product. So earlier, we calculated that the delta H for the reaction for joining of hydrogen and oxygen into water was negative 572 kilojoules. Therefore, it goes into the chemical equation as a product. So we're going to have 2H2 plus O2 goes to 2H2O plus 572 kilojoules. Okay, now note that the plus and minus sign just tells us which side to put it on. When we actually put it into the equation, we only write it as positive. Okay. So now that we have this in our equation, we can actually use it with stoichiometry. So, so let's take our equation. Now let's say that we have 5 grams of hydrogen and we use all of it up in this reaction. How much energy will be released? Well, again, we can just use stoichiometry. So we start out with 5 grams of hydrogen, and we always put our starting one over 1 since it's all a fraction. So then, looking up into our periodic table, we can see that 2 grams of hydrogen gives us 1 mole of hydrogen. Okay, so there's 2 grams per mole of hydrogen. So we write that as the second one. And then, if you look at the equation, the coefficient by H2 is 2. So we have 2 moles of H2, and on the right, we have 572 kilojoules. So 2 moles of H2 correspond to 572 kilojoules. And so when we multiply it all out, we get 715 kilojoules as the final amount of energy. So, in sum, reactions are exothermic, which means they release energy or have a negative change in enthalpy, or they're endothermic, which means they store energy, they absorb energy, or they have a positive change in enthalpy. We have 2 ways of calculating our change in enthalpy. We can calculate it with the bond energy, and that'll take the sum of all bond energies in our reactants and subtract the sum of all bond energies in the products. Or we can do enthalpies of formation, and we can take the enthalpy of formation of the products and subtract the enthalpy of formation of the reactants. One thing to notice is that those two are that in those 2 equations we reverse the position of the reactants and the products. Okay, and that's important because if you get that wrong, you'll have the wrong sign at the end. And then our delta H, the sign of the delta H tells us whether to put the energy with the products or with the reactants. And so if it's negative, then the energy is actually a product. and we write it as a positive number on the product side. If the delta H is positive, we write it on as a positive number on the reactant side.